tell her about some of the research she's doing as part of her PhD. Okay, so if people online have questions, just type them in the chat and I will read them out at some point later. But yes, please go ahead.
All right, so hopefully you can hear me online as well. If not, let me know. We can try something. Yeah, so hi everyone, thank you for coming today. Yeah, this is my PhD research, and then yeah, this is my PhD research that I'm doing at McGill, Canada, but I'm also doing part of it there in Frankfurt. So this is about cooling neutron stars, so it's a mixture of astrophysics and nuclear physics. You can also online stop me anytime you want with questions, and I'll ask in between the presentation. It's all good. All right, so this talk is going to be based on those 2 archive papers that we published. There's another one we're writing with more studies on quarks. That's mostly what I'm focusing today. Yeah, of course, in collaboration with Professor Baruch Fatoyev, Jan-Erik Christian, and Jürgen Schaffner-Bielisch. And this is also partially funded by MyTex and the Schlumberger Foundation. So I've talked about everything, so let's go on. Okay, or not.
You might have to click into the document one time.
On the slide.
All right. Sorry about that. Okay. So the motivation of this research is basically to study neutron stars, to study the core of neutron stars, what's in there. And of course, you know, this is a very complex environment because we have very dense place submitted to high temperatures, could be or not, submitted to high magnetic fields. There are lots of things going on. And we kind of have some idea of what's going on the crust because the densities are not so high, but it's really hard to understand what's going on in the core because it's an environment that we're never able to reproduce in terrestrial configurations. In particular, I want to point out to you that we don't know the composition of the inner core of neutron stars. So are there strange particles? Are there quark particles? What is going on? What about superfluidity? How can we even describe in-media interactions on that place? So this is the basic motivation for us to study this research. But put another way, we also want to understand the phase diagram of KCD, which would hopefully let us know about everything, how matter is organized, both in the hadronic phase, which is like matter as we know it, but also in like phases of higher temperature that we can maybe sometimes just reach in the early universe, so with particle accelerators, or even like at high chemical potentials, there are environments we can only reach in, for example, neutron stars. So ideally, one would know exactly how to describe matter in all those phases. When we're talking about equations of state. So want to populate this diagram with equations of state that let us know how matter behaves in all regimes of temperature and density. But actually, this diagram here is just a simplification because in reality, and this is a slide from Veronica Dexheimer, and also this great talk, in reality, it's not just about temperature variation and chemical potential, but also some other stuff that's going on. So for example, charge particle difference, so as we call isospin asymmetry. So in neutron stars, not only the temperature can be changed, the baryon potential, the densities are very high, but also there's an asymmetry between the numbers of neutrons and protons. So this is just a third axis that we would like to put there in this diagram to add this complexity, let's say. If you want to go be more precise on this description, you can add more x's there corresponding, for example, to strangeness. So in other words, when we go to higher temperatures, maybe higher chemical potentials, higher densities, there could be some strangeness going on. So there could be multiple x's in reality to this phase diagram that I just showed you. And of course, we can somewhat easily populate this diagram with several equations of state, both built from microphysics, so first principles, so just looking at the interactions between mesons and pions, for example, to mimic for the KCD, or you can just build empirical equations of state, for example, that you just put the parameters there somehow freely to make sure that they match the descriptions of matter in the regions of temperature and density that we know, that we can reproduce in the laboratory. So this is basically the name of the game. 2 challenges. From one side, you want to construct an equation of state that makes sense, first principle calculations that correspond to the interactions that you would hope will happen. And also you want to make sure that those equations of state will reproduce the properties of low energy physics. So this is physics as we know it on Earth. So for example, the binding energies of nuclei, the neutron skin of nuclei, for example, This is a challenge. And the other challenge from the point of view of astrophysics is to make sure that this same equation of state will also reproduce the properties of matter in a very high density environment, such as neutron stars. And this is like a macro physics challenge, because when you go to neutron stars, we're talking about, for example, mass and radius measurements, which are things that we can hopefully measure with somewhat good precision nowadays. So you see the challenge is both a microphysics and a macro physics challenge, both a nuclear theory, let's say, nuclear physics challenge and an astro challenge. So, okay, and hopefully I have by now convinced you that there are several equations of state available in the literature to describe all of those things. And there are several ways of building those equations of state, several equations of state available in the literature that also reproduce the data that we all know should be reproduced. So in here, I'm just showing you an example of some equations of state. So those are all relativistic mean field equations of state. So this is one way, one technique of building equations of state that basically, as I said, mimic the interactions of particles. So we're talking about like describing QCD, but of course we don't have the proper machinery. So we just say, okay, let's mimic that instead of a quark and gluon interaction, the particles are interacting through mesons and pions and so on. This is how you know, it's not very accurate, but it's good in a certain limit of density. So this is how you do it. And to, let's say, put the strength of the interactions, we have those potentials, G's, and so on. And you can set those potentials to some value. So this is a bit, yeah, you're going to put this by hand, in a sense, the value of the potentials to make sure that the properties of the nuclei are being respected. So as I said, binding energy and so on. So this is one technique of building equations of state. I'm not going to go much into details, just so you have an idea. There are several other techniques you can build, but I just want to show you here that even if you just focus on one specific technique, that you have a limited amount of freedom there, you will still have lots of equations of state that are still able to reproduce all the data that we're talking about. So both in low energy physics, but also astrophysics, mass and radius here. For example, we have several equations of state here. That this is not all of them. This is just an example, some of them, of just one technique, and they all obey, most of them obey like nicer there, for example, and the maximum mass there. And you can always build equations of state that, for example, if we measure as slightly higher massive neutron star, we can always build another equation of state that will just adjust to that other data. So this is a bit, this is the bit of the state of art where we're going with that. Okay. And this is just, again, so those are just, this is just one technique, and this is just for the most simple equations of state that only have neutrons, protons, electrons, and muons. So the most simple you can build. As I said, you can have strange particles there as well. And this is not even included in this picture I'm showing you here. But it could be, for example, if you want to. So this is another diagram of mass and radius that I just showed you, but now we have equations of state that are both hadronic and also with a quark phase. So you can see those branches that look a bit like horizontal there. So those are the branches that will have some quarks on it. So again, we are putting by hand this. We have some hadronic equation of state. You say, okay, at some density that I'm just going to choose, informed guess, let's say, at some density that's going to happen at phase transition to quarks. And let's see if those new equations of state can even reproduce nicer measurements. So this is research that has been done already by my collaborator there. Yeah.
Why do you have so many equations of states? What are the parameters that add to their volume to have so many equations of states?
Right.
Can you just repeat the question?
Yes. So the question was, why do we have so many equations of state? What are the parameters for those equations of state? So the parameters that are there depend on the method that you build the equation of state. So for example, relativistic mean field that I'm just talking about, the parameters are the strength of interactions between the mesons and pions and the other particles that are mimicking the QCD interaction. So those are the parameters. It's called G. Depending on how you build it, there are some other parameters that you can choose. So for example, if you have more interactions or less interactions, then you have like more parameters, less parameters. So this is really, it really depends. And why do we have so many? Well, I guess we have so many because we all know those are all, let's say, approximations in a way, right? So we can't really calculate from first principles all the behavior of matter in all that phase diagram, in all temperatures and all densities. It's really computationally hard. We have the sign problem, for example, lattice QCD. So lattice QCD is like a way of doing this, but like computationally. So just put everything there in the computer and make it calculate. And then we have some problems with convergence there that make it work for really, really high temperatures and high energy density, high number densities, but not exactly in the point of neutron star. So we have like data constraints from low energy physics that put us in that left-hand side of the diagram, low temperatures, low number density. And then we have some computational results. They're like high temperature and high number density. And in between, it's hard to access. So then we have that many equations of state because we're trying to bridge those two things, to connect those two regions in a way that is consistent. But then there are many possible ways of doing that, many possible techniques, and some of them, a reasonable amount of them, matched the data. But it was worse. So in the past, for example, we didn't have nicer. There were way many more equations of state there. We thought, well, this could be it. But then the more measurements we have on mass and radius simultaneously, and also tidal deformability, and hopefully cooling as well, the more we restrict the phase space, the parameter space, and the more we get to like, okay, this equation of state has to be around here in a certain parameter space. And this is the name of the game. This is what we're doing, trying to get as much data as possible, understand it in a way that we can constrain that parameter space.
So basically, the parameter is like in between. There's degeneracy.
Yes.
People usually just kind of settle on one for computational reason, and then that's what you get from.
Right. So the question, yeah. So the question is if there's a degeneracy in between those two regions of like low temperature and high temperature and high number density. Yes, exactly it. So we know a little bit here and we know there, but then bridging that is really hard. So even like, so there was a paper that they were, I think, I don't want to say the names wrong, but there was a paper recently that they just said, okay, let's just do computationally then. Let's just build, no matter the microphysics, let's just build any number of equations of state between there that, obey those two limits here, and let's see what we can make of it. And there's still, I mean, they got some results, they were interesting, but there's still a great degeneracy. It's not that they could say, okay, this is definitely the equation. No, there's still a region there. Basically because of data. Yes.
This relates to this discussion, and we have already interacted with. So, why conceptually do you expect one and only one equation of the state? Because if you look at the stars, right, the composition is different, and the state of the matter is different. So, what's behind expecting only one equation of the state?
Right. So the question is, why do we only expect one equation of state to describe all this region, right? This is a polemic question, and this is, I guess, an open question. One could argue that maybe not, right? One could argue that maybe the equations of maybe what the matter inside neutron stars is so very different that it's really something else entirely. I guess the most strong argument I've heard in the sense of like why there's only one equation of state is that like Occam's razor, like why would it not be? Like if we can describe matter with one equation of state and there's nothing pointing us that we couldn't, I mean at some point, if we see something that definitely is completely off the records, like we cannot even, then maybe you'd say, okay, and maybe we should think about this. But right now, all those equations of state that I showed you here, they are still able to do that. They're still able to reproduce low physics and also neutron stars. And also you can extend that and they even reproduce perturbative QCD as well. So at this point, I would say maybe there's nothing moving us towards that. But if we measure like a neutron star that has like very different properties from what we've seen, then we could go there. Yeah. Okay, so I'm gonna move on. Okay, so the whole point of this was we have several equations of state and we have several data that we can use to help constrain those equations of state parameter space. So both low energy and both in astro, mass and radius. So I call like structure constraints as mass, radius of neutron stars, tidal deformability, those kind of macro properties of neutron stars. But then there's also cooling. So this is a bit more complicated because when we can obtain the luminosity measurement for a neutron star, but it's harder. I argue that even though it's harder, it also gives us very important information on the microphysics of neutron stars, because each luminosity, so when you measure a neutron star, we measure like an external temperature, for example, when you can correlate that to the luminosity of that star. But what really is the luminosity are the internal processes inside the star that are emitting photons and neutrinos. That's what's really cooling the neutron star. So you see, if we know all the processes that are there, then of course we know the composition of the neutron star, right? So what we measure is the temperature, but what we try to guess is the processes that are happening inside that star to give that value of luminosity. This is tricky because then you have to consider every single process. And as you can see here, this plot shows the luminosity and the age of the star. You can see that the error bar, so each like rectangle square is like an error bar in luminosity and time. And you can see sometimes it's really large. So it's a bit of a hard thing to do in isolated sources. And there's also, so isolated sources are just like a neutron star that's there. But there's also, of course, transiently accreting sources. So those are neutron stars with companions. So they're orbiting something else, and they're transiently accreting mass from that companion. And then we have something similar. We have the luminosity, but then the average of accretion, average rate of mass accretion from that companion. And then again, we have some problems with error bars. As you can see there, we have some errors there. So everything that you see here that's just arrow instead of just cross, the error is just upper limits, both on luminosity or mass average accretion rate. Even though if we see something, for example, a star that is cooling very fast, then we have a little stronger hope that we can get some constraints on the microphysics of the equation of state from this kind of data, because, and I'm going to show you in a while, but fast processes cannot always happen in a neutron star. They only happen above a threshold. So if we see a neutron star that is very cold, then we guess, okay, there's a fast process going at to cool that so fast. Therefore, the equation of state is above a threshold. So that gives us some information about the equation of state, and that's pretty cool. So I'm going to tell you exactly how this happens now. So again, take the most simple equation of state you can think of: neutrons, protons, electrons, and muons. And this is one of the fast processes that are cooling the star through the emission of neutrinos. Right? So those are two pairs of reactions there, something that looks like a beta decay and then a proton capture. So we have those two reactions because we know that the chemical composition of the star is not happening. So even though, so some neutrons are decaying into protons, but we know the other reaction has to be happening as well, so that the chemical composition inside the star is not changing, but the neutrinos are being emitted, and that's what's really cooling it. So if you look at those reactions, maybe you just see it right straightforward that they can't happen unless there is energy momentum conservation. And this is where the threshold is coming from, right? So this expression that we see there, YP, is just the threshold above which there is energy momentum conservation so that those reactions can actually happen. Okay, so this is one piece of information. And the other piece of information is really the emissivity. So what is the rate that neutrinos are being emitted according to those reactions? And then you can calculate that quite straightforward with some Feynman diagrams, and then you get that expression there. You see it's a function of several constants, but also the effective masses of neutrons and protons. So this is just not the bare mass of the neutron and proton in the vacuum, but the mass that, let's say, the other particle sees because of immediate interactions, right? So this is the signaling that this process is not happening in the vacuum. So this is how you have like two pieces of information from just this one process, right? Have the dUrca threshold. So if this thing is happening, then the equation of state has to have a proton fraction above a certain number. That's good information on the equation of state. And then it gives us some information on the effective masses there, neutrons and protons as well. As I said, this is just one process in a multitude of processes that are happening. So reactions like this are just for the hadronic. So this is just, I just showed you hadronic direct Urca cooling, but if you have something strange, like some other particles, some strangeness, I mean, some other particles, then anything that cools and emits neutrinos through those kind of reactions are direct Urca reactions or fast reactions. And the same thing, you have to do it again. You have to calculate the threshold again, and the emissivity is going to be based on certain effective mass of those constituents there. Okay, so this is the first table there. Fast processes. Down there, you have like an example of slow processes. So again, as I'm saying, we only measure the luminosity, but in reality, all those things are happening at the same time. So maybe there's some fast processes, but even if they are not there, there's some slow cooling processes. So for example, modified Urca reactions, they are very much look like the other reaction we just saw, but now with spectator nuclei. So that means that we don't have to worry about energy momentum conservation anymore, because those spectator nuclei will make sure that this happens. But then those things cool the star a little bit slower. But anyways, they're always there. And then we have some other stuff going on, Brane-Strahlung reactions, you name it. Anything, all of those things are happening at the same time. And of course, if you have strangeness, then those processes are happening with strange particles as well. And quark matter, same thing. Okay. So what we do, oh yeah, also don't forget superfluidity that I was almost forgetting. But if you have some superfluidity, then basically think that the number of free particles that would be available to react and emit neutrinos for those reactions is now reduced, right? Because now there are no more free particles that are going to be tied together with like Cooper pairs. So you have to take that into account, and you have to understand that whenever there is superfluidity, then those rates are going to be reduced, exponentially reduced, in fact. So this is very important. So looking at this all right now looks a bit abstract perhaps, but when you code all of this together, you see the difference. And this is something I'm going to show you in a second. And again, the trick here is remembering all those things are happening at the same time. So I just have the total luminosity of the star, but I have to account for the fact that it might be cooling for fast processes. So the equation of state, it might be above a threshold. Even there may be some superfluidity, and if there is, it's going to be reduced again. So it's a game of putting all the contributions there and then just getting the final result. But really getting the final result and then comparing with what could be, right? So this is a bit of my work, and this is what I'm going to show in a second. But I just simulate a bunch of equations of state, bunches of gap models. Are there quarks? Are there not quarks? I just put like, is this process active? Is it not? I just put all of these things that could happen, and then I calculate everything, and then I compare the data. So I say, is this case possible? Okay, what about this case? What about this case? And hopefully this gives us some information about the equation of state and superfluidity. So you can see it's a degenerate problem in a sense that I'm trying to figure out too many things at the same time. But it's interesting, especially, for example, if you look at quarks, for example. So as I said, if there are quarks, then there is some emissivity of neutrinos for quark processes, very similarly to what I just showed in the hadronic processes. Now there's a function of the strong coupling constant, which is a function of density. So again, something that we don't really know that much, and a function of the mass density there. And the game here, the idea is, okay, so if I know there is some quarks, then this process is going to be active. But I don't know. I don't know in reality if there are quarks in the equation, in the neutron star, right? So what I do is I'm going to put some quarks at some transitions densities. I'm going to compare with the luminosity cooling. I'm going to put in the cooling and compare with the luminosity data. And then I'll see, well, is this phase transition consistent with this data, right? And this is the game I'm playing.
So excuse me, what is raw mass?
Raw mass is the mass density. So the mass density.
How do you get it from the Fermi momentum?
I get it from the equation of state. So I have an energy density there, and I divide it by c squared. That's the mass density. The mass density at some point in the star. Yeah. Okay. So, okay, this is a lot of information. So just a quick summary here. Cooling data can provide microphysics constraints in a way that other measurements cannot. So if you remember, you have a mass and radius, that's all you get, but you don't get really the composition of the equation of state, right? So this is interesting from the point of view of cooling. It breaks a little bit the degeneracy. Neutron star equation of state must account for both slow and fast cooling sources. So as I said, all processes are happening at the same time. And in the end, we have really to make sure that this equation of state, this framework describes both stars that cool very fast and both stars cool very slowly, because we've seen all of those stars, so we know they exist. So have to allow for high luminosities, relatively high luminosity, relatively low luminosities, has to include all of those things. And we can achieve that with fast processes with like a high proton fraction to achieve that direct Urca threshold, but we can also have strange particles, quarks, and so on. And of course, don't forget superfluidity that always makes our life a bit harder. Okay, any questions here? All right. Okay. So now I'm going to go over a little bit more technical details of the equations of state that I used and how I exactly do this work. So as I said, I'm going to work with relativistic mean field, and we've been working with relativistic mean field equations of state, the most simple case, only with protons, neutrons, electrons, and muons. And that already gives us a lot of equations of state. We can always parameterize that equations of state in energy density, a part of energy density that it corresponds to symmetric nuclear matter, so matter that has both same numbers of neutrons and protons, and this asymmetric part that corresponds to the part of the energy density that has different numbers of neutrons and protons. And that second part there, we have some parameters, J, L, you see there. This is just really a parameterization, and it's just a way to understand how the energy density changes if you have like high densities or not. It's very interesting to use this parameterization because this value L there, this slope of symmetry energy, is one thing that low energy physics measurements can hope to measure. So this is something that has already is going on right now. So in the laboratory, they're measuring this value of L with lead and calcium. So this is nice to have this parameterization because you can say, okay, if they didn't tell us what the value of L is, we put it here and we get some results on neutron stars and vice versa, right? We can hope to inform one another. Yeah. So those are some of the equations of state I'm using. So I'm changing this value of L from 47 to 112. So it's very broad. We don't really expect, in this parameterization, we expect the value of L to be just one value. So, but we don't know at this point. So I'm just changing from 47 to 112. You can see that different values of L make the equation of state stiffer or softer, depending where you look for. All those equations of state I'm using here, they obey nicer constraints and also the maximum mass. So on structure, we're good. And again, you see, you go to the problem again that we have too many equations of state that feed the data well. And they also fit the low energy physics parameters as well. But what is really interesting, so if we just working with structure constraints, you get to this point of, okay, cannot say anything else about those equations of state. But with cooling, we can actually say something more about those equations of state, because now each equation of state will give us a different value of proton fraction. So the dUrca threshold that I was mentioning is going to happen at different densities, depending on the equation of state that you're using, okay? In other words, we're going to see smaller neutron stars cooling faster, depending on the equation of state that you use. And our hope was to say, well, maybe we get to such a low mass that this equation of state can be ruled out, right? Because we wouldn't expect neutron star to have a mass of 0.2, for example. Okay, so this is where we're going with that. This is the superfluidity models. So superfluidity is basically telling you when is the density where it's more energetically favored for neutrons to pair up. What is this energy? So this is what those plots are telling you there. This is the x-axis, KF. And then the y-axis is delta, which is just this amplitude. So maybe the strength of superfluidity. So yeah, so this is a function of temperature in a sense. So what is the density where it's more energetically favored to pair up is a function of density, is a function of temperature. This is what you're seeing there. As you can see, so there is expected to have some superfluidity on the crust, but I'm not doing with that. I'm just analyzing the cooling of the core, because that's what's going to be more important for the neutron star. But in reality, if you want to do the proper thing, you have to consider the cooling of core, crust, and then superfluidity of the core and the crust as well. So here you can just see the superfluidity of the core. Then there's going to be some superfluidity in protons and some superfluidity in neutrons. You can see that the protons curves, the ones here on the left, they look more or less close to each other. Temperature varies a little bit, but versus the neutron one, that's all over the place. And that's really a reflection of our ignorance and the superfluidity. You know, those calculations, if you have an equation of state, you can just do, for example, a BCS approximation and find out that. But the BCS approximation is only valid in mediums with low density, sorry. So that's not valid for neutron stars. So basically what we do is we can use the BCS calculations, but then we know it's not going to be valid in neutron stars because it's a medium high density. So What people usually do is they put some free parameters there to account for those median contributions. And because we don't know how they affect the amplitude and density, it really can be anywhere. So that's why you see these different families of pairings there. So those are all pairings that are available in the literature. As I said, no one can tell which one is the right one. So I just said, okay, let's gonna work with all of them and see if we can, from our method, kind of rule out some, or at least get a better understanding. Yeah, and of course, don't forget quark phase transitions. So on top of all of that, that could be quarks. And this is just one example of a phase transition there. So the dashed line is just an hadronic equation of state, normal, as I just mentioned. And the solid lines correspond to hybrid. So there's going to be some quarks in the solid lines there. As you can see, the transition is happening for the same density in those two cases. And the difference is just this delta E, so the gap on energy. So there are many ways you can build a quark equation of state. You can build from first principle, same story. But for this specific work, what we're doing is we're not going to spend too much time doing this. And we want to work with something easily parameterizable. So we're saying we don't know exactly how that quark equation of state has come to be, but we know that it's happening at this transition density, and it corresponds to a certain gap in energy density as well. So that's all we're saying. Okay, and we're putting this by hand in a way, but still making sure that both in the hadronic and the mixed branch, they all the astrophysics constraints are being obeyed, nice or maximum mass, all of that. Okay, but you can see it's still many equations of state in the end. So the first, so the very first, I'm going to the results now, brief. The very first study we did was just with the hadronic equation of state. Again, the most simple possible case. And what's happening basically is explained in this diagram here. You can see that there's a maximum density there in the middle of the star. As you go to the crust, the density is getting smaller. At some point, you might cross the dUrca threshold. And that means that all this area from the center to the dUrca threshold is emitting neutrinos through dUrca reactions, through fast reactions. And then we have some crust and etc. So what we really want to see here is what is the volume of this region that can emit neutrinos through dUrca reactions to describe the data that we are interested in describing, right? To compare this with data. So can we build a star that like really emits that amount of dUrca, and is like, what is necessary, right, to reproduce the luminosity we're looking for? Do we have to have a huge core emitting dUrca all over it, or just a small part is enough? So this is the question. And you can see that the answer to this question is in this plots down here, and depends on the value of the L of the equation of state for our parameterization, right? So this is another advantage of using that L parameterization. Depending on the value there, you have certain amount of the core emitting dUrca, because like, as I said, dUrca threshold, that YP, is a function of L. So we will basically see that low values of L have a high dUrca threshold. It means only very massive neutron stars are emitting the neutrinos fast dUrca reaction. So this is like this part here of the plot. So this is basically telling us, if you just look at this, it's basically telling us, okay, low values of L can describe fast cooling stars and slow cooling stars. We just have to make sure that these are within the mass ranges. So we're just saying basically fast cooling stars are above 1.8 solar mass, because dUrca reaction region, and slow cooling stars are below that. So all good. That would automatically rule out the most the higher values of L here in the equations of state, right? Because we're saying, well, basically all neutron stars are cooling are fast, and that's not true because we see there's slow cooling. So we basically just looking at this plot, we would just say, okay, whatever, all those equations of state 70 above, just rule out, and life will be so easy. But no, because we have superfluidity and that changes things. So basically, there's the same thing I just said, but now in the plot of what is the mass of the star that corresponds to the luminosity of this one source. So there are so many free parameters. We thought of focus just in one neutron star at this point. I know there are other studies that people just do this for all neutron stars, all luminosities. And usually people do this with Bayesian techniques because there's so many things going on. So we decided to just focus on one neutron star, which is this MXB there. It's one of those low cooling, and it's one of those that have really nice error bars, just upper limits. So that's good. Of course, we also had a study on how, so before I published this paper, my supervisor published this other paper on how we could translate the temperature that we measure, superficial temperature, to the temperature of the core. And this is like a function of the envelope composition of the neutron star as well. So there's another degeneracy there. And we chose that star specifically because we had studied in very detail. They were able to say, okay, the luminosity must be within this error bar there, which is what you see. This blue arrow bar is basically all the luminosities that they could be for that temperature that matches the data all nice. But it's a very intricate thing. It's not something we can do with all stars, exactly because we don't have that precise measurements of temperature for all stars. So that's a bit tricky. But anyways, we thought, okay, we only have one data point, but still we can make some, get some results for those neutron stars, for those equations of state, and we can maybe get some understanding of what this means to other neutron stars, right? Under those equations of state here. Of course, we have to put, oh yeah, so and we also did for this other source, SAX, which is much colder. And this is the problem I was telling you about. We don't really know the temperature that well for the source SAX. So we have like much higher error bands. This is a plot for like one temperature, but this temperature could be between 28 and 40 EV. So it's really a family of plots I should be showing you here. But then that's harder to understand. Yeah. Yeah, so the question is where the temperature comes from. It comes from, yeah, this power spectrum analysis, I believe. Yeah. Yeah, but then, okay, I'm not an expert on that, but then there's, yeah, I know it's a bit complicated because you can fit that for a black body, but sometimes it fits well and sometimes it doesn't. So you have to put some, yeah.
I think this first number is like it has like biases, so it's not fitting. It's basically a power. Like
Yeah.
So I guess it must be very hard to find like probably you can fit a black body now, like it's significant or anything. I mean, that's more an observer point of view question. We can discuss a little later.
Yeah, exactly. All right. Yeah, you'll probably teach me. I didn't ask you about that. But indeed, so there is this difficulty in measuring this temperature, and then in converting this temperature to, like, depending also on the envelope composition, to something that is the more accurately the temperature really at the surface of the star versus the surface of the detector or whatever. So okay. Now, how superfluidity ruins things a little bit. So remember this lovely parameter space, we had all those things here, all this region that was allowed to have direct Urca, and we said, oh, let's just ignore all this, or we'll start, those equations of state won't even. But now if we have superfluidity, we're basically saying, well, for this specific superfluid model that closes up here, we're saying all this region that before was allowed is still allowed, but now is exponentially suppressed, which means that we basically save all those equations of state because we say, well, whatever. Now they can really describe really fast cooling stars and slow cooling stars, because then you just have to make sure it's very exponentially suppressed, so much so that we can hardly see the effect of that direct Urca.
Another 10 minutes.
All right, so okay. So I have 10 minutes, so I'm going to speed up things a little bit. So okay, so we did this analysis now considering all superfluidity models that I just showed you, is in total 17, and we have to make sure that they're both happening at the same time, right? So because this one is a simplified diagram here, and I'm showing you just if there is only neutron triplet superfluidity, what are the predicted masses for this one star, right? But in reality, things are even more complicated than this because I have to account for proton singlets and neutron triplets at the same time, and that changes a little bit. And you can ask me if you're interested. I have some plots there for specific combinations that are interesting. But basically, the idea is, okay, let's say we have something like this here. Can we at least rule out some superfluidity models, right? And of course, here we're going to be able to see that, again, the idea is this one star has to have some mass that would allow for colder neutron stars to be explained, and also hotter neutron stars should be explained. Okay, so the mass of the star cannot be very low or very high. So basically, this is the idea. And then you can see that maybe for like low values of L, everything is okay, everything is possible. But then if you go to like higher values of L, perhaps this one model here, the green one, is bad because now we don't have that range in masses that I was telling you about. So this one cold neutron star has a very low mass. What about the hotter ones? We can't explain with those configurations. Again, as I said, the real picture is a bit more complicated because I have to take into account triplets and singlets at the same time. But if you just like, I'm just showing you this so you can like understand what is the kind of analysis that we make. In the end, we are able to indeed exclude some combinations of gap models for some equations of state. So what happens is the result ends up being something like high values of L for this PS and this NT model, superfluidity models are favored. This is the kind of result that we have with this analysis. Yeah, so perhaps repeating a bit of what I just said, I'm not going to reread this. I'll just stop here a little bit, ask if you have questions. No, all good? All right. So yeah, so this is the research that we did for this one star, MXP. Of course, we have to take into account other stars as well. And this is just the hadronic equations of state. So if you, every time I give this talk to people who are working with equations of state, they say, oh, try my equation of state. Yeah, what about this other? So this is something we can be doing for a really long time. We get some constraints indeed, basically in the form of like, okay, this equation of state and this superfluidity does not agree with data. So we can rule out and reduce the parameter space a little bit. I'm particularly more interested, oh yeah, we have some words on heat capacity as well, but I can talk about this later because we don't have enough time, and I'm really excited to tell you about Quark. What we're going in this direction now, and the research that I'm doing in Frankfurt is basically looking at those equations of state that have quarks, the hybrid ones, specifically the ones that you have like this mass radius diagram, 2 branches, we call twin stars. So I'm specifically looking at those equations of state. Of course, you can have hybrids that don't look like that, but we're focusing on that because the signature is so different, right? This is one thing that if you see a mass and radius, like 2 stars with like same mass and very different radius, this is like a smoke signal for twin stars. This is like the closest we could ever be to get smoke signal for, okay, there is some quarks in this star. So we focus on that. And we want to say, can we constrain the phase space a little bit more in the phase transition, right? Because as I said, we put the phase transition to quarks, they do it by hand randomly, okay, but still describes the data, but it's a bit random, like there is no physical reason for why the phase transition is here or there. And I'm trying to constrain this a little bit more of cooling. So basically this is the scenario we're looking for. There's a little bit of quarks in the core of neutron stars. And then the hadronic part could have, again, fast cooling processes or not, depending on superfluidity, depending on the hadronic equation of state. And basically, ideally, we would look at something like this or something like this, where the dUrca threshold is never reached. So we can just look at the quark influence on the neutron star and say, okay, can a star like this describe the data? What if the phase transition is lower? What if it's earlier? Like, can this describe the data? So those are the preliminary results we have. Again, this is for MXB, and this is the simplest case. There is no superfluidity, so nice. And I'm working with 2 equations of state here, 47 and 112. And what we see basically is, if we have a phase transition to quarks at saturation density that's super low, that's not something we would expect. I just put it there just to explore the parameter space. So at very low densities, you have a phase transition to quarks. Up to like the 6 times saturation is a very high density there. Can we reproduce the luminosity of MXB? And then what's the mass of that star that reproduces the luminosity? What is the dUrca fraction, right? So we basically see that if there is hadrons, the hadronic cooling will always dominate. So this is perhaps not new, but this is a bit frustrating to us because like all these points here that are on plateau, they're basically just the hadronic cooling. In other words, if there is a quark phase transition, at those points for this equation of state, we cannot see with cooling because the hadronic will dominate. We can't see. We're not saying that it doesn't happen. We just say we can't see. But some cases we can see. So for example, those points here. Again, remember this is very low L. And I was saying, well, only high mass stars will emit through that. But now we have quarks. We're basically saying that a quark emissivity is able to account for all the luminosity of the star. So if we, for example, happen to measure the mass of MXB, and it's a very low mass, this is an indication that's either a very high L hadronic, or there is a phase transition to quarks pretty early on. And that's super exciting. Yeah. So basically that is that. Again, quark dUrca dominant is only dominant if there is a phase transition before the dUrca, the hadronic dUrca threshold. So this is a bit of a play. Again, the degeneracy there. Sometimes we are able to see the phase transition, sometimes we're not, depending on the combination of hadronic and dUrca and all that. But there is a possibility of really constraining that phase transition with cooling, and that's pretty exciting, especially now that we're going to get, we're expected to have like more structure constraints. And I feel like if we combine the structure constraints with the cooling constraints, I think we're going in a good way. I mean, there's a lot of work to be done there because we have all this modeling of temperature on the observational side, and also on the microphysics side, incorporating all the processes there in the code is very tricky. Have to account for difference in temperature, immediate interactions, and so on. But I think it's really interesting. I think it's a good way to go. Of course, I just show you that here. And this again is very simplified because there is no superfluidity, there is no color superconductivity. So similarly to what happens in the hadrons, quarks can pair up if it's more energetically favored. This is something we're studying there in Frankfurt a little bit as well. But also there is no mixed phase in this scenario here. So it's either quarks or hadrons. But in reality, that could be a little bit of mixed phase in the core of neutron star, quarks and hadrons. I just, for this one specific case, it doesn't change that much, but it could. So there's something we would like to understand. Finally, this is a very, very last slide. So hopefully I was able to convince you that luminosity observations can constrain the equation of state in a tricky way. You have to think too much about it, but it is a good alternative, especially when you combine with structure constraints. Also, in this research, we're able to really prove that full hadronic equations of state can describe cold neutron stars. This is, again, not just me, some other people are doing this out there. But this is actually a question, right? An open research question. Are we even able to reproduce all the luminosity that we see with hadronic neutron stars? And so far, yes. We'll see later. For me, some large values of L seem disfavored for the equations of state that I used. Again, I can only talk about combinations of L and superfluidity gap models at the same time. But this is better than nothing, and this is something. So this is good. Also, certain hybrid equations of state with quarks can fit other observations. And this is particularly interesting when you do structure. So like some quark equations of state, some hybrids can even describe like mass and radius that we measure nowadays. So this is nice. But we can hopefully get some constraints on the phase transition if we analyze cooling as well. So this is a work I'm still doing, and hopefully I'll have a paper this year so you can read all about it. And that's it. Thank you.
Okay, we already had some questions, but are there any more from the room or online? You can unmute yourself or write them in the chat. Yes,
Yeah, very, very interesting. I worked in the past in all the superfluid quark cases. And a related question, because you are mentioning that when there is superfluidity, then there's exponential suppression
Yes.
processes. But I remember in the superfluid quark phases, you also have other channels provided by the light modes that have in the superfluid phases, like superfluid forms. And people have studied that in quantum matter phases, and I suppose that here you may have also a similar channel. Have you ever considered those?
Okay, so
So you may have superfluid forms that automatically also interact with the neutrinos
yes.
and so.
Okay, yeah. So super interesting. She's talking about like some other ways superfluidity can change that in like other channels, yeah. So I've heard about that. I haven't included that in this code right now. But yes, indeed, it can happen, you know, like, so for example, one of the things that I haven't included, but happen when we have superfluidity is we have an extra process that emits neutrinos, which is just the act of pair and break formation, they call it pair break formation. So there is a formation of Cooper pairs, the same way that we had like beta decay. So the formation of Cooper pairs and the breaking, that effect can generate some more neutrinos, and that increases the luminosity. So in a way, having superfluidity reduces the luminosity, but also increases for this other process. And there's like a bit of a game of how much does that compare what wins, the increase or the decrease. It happens that the increase is important only around the critical temperatures. So this is one example. So as you said, there are other things that can happen. I haven't included that, but it's something we have to be aware. For the quark phase, I know there are two possible phases. I mean, okay, from the research that I've seen, two possible phases for color superconducting. We have the phase that up and down quarks are pairing, and then we have this other phase that strange quarks are also pairing. And then the locations of these two phases are different, and the effects they have are also different, because if you have strange quarks paired up, pretty much you have no cooling anymore, because you're pretty much suppressing all the reactions that could emit neutrinos. So this is something we have to take into account for sure. As you can imagine, it's very model dependent, I would say. Each model will have a different superconducting phase and the location there. So yeah, so in the end, we end up just being able to say something about that one specific equation of state for sure. That's why also I didn't want to do that too much in this research right now. We're just saying, okay, let's not do the color superconducting phase, because in the way, perhaps there's a region there in the phase space that there is no superfluidity yet, but there's still neutron stars, right, around. So right now we're not doing that, but for sure, in the future, there's something we have to take into account.
Any other questions? Yeah, go ahead.
Yeah.
Thanks for the nice talk.
Thank
I
you.
had a question about the choice of targets. If there was any reason why you should especially these two sources.
Yeah,
Because
all right. So, right.
Just want to say the question again.
Okay, yeah, so the question is, was there a reason why we chose the specific targets? So I guess MXB and SAX, right? So yeah, so MXB first we chose because it's right in the middle of this plot here. So this is like a low luminosity, so yeah, low luminosity, but it's not the lowest possible. So there is like room for speculation there. Also, it has a very good error bars, right? It's not like upper bars, so it has a good measurement, specifically that one. And then we had this other study that my supervisor did, and like carefully understanding where the sources of error could come from there. So, okay, this is like a no-brainer that we're going to start there, pretty much. Then SAX we chose because it's number 15 there. Is it? No, sorry, it's number E, is letter E there. So it's this guy here. We chose that because it's the lowest and the coolest measured, and you see it's even like an upper limit there. So this was the reasoning. My code right now only has fast cooling processes, so everything that is slow, I can't do it right now. I have to incorporate the processes. So that's why we captured the slow cooling, and also because we're hoping to get more constraints there. But basically, this was the reason. But like between E and 10, for example, I don't know, like 10 looks like even more upper limit. You see, like this is a bit of a, I want to do more stars in the future for sure. The problem of doing like the stars in the region of 7 is there's only like a speculation, like, oh, can this question of state get like colder neutron stars? But I don't really have the numbers to run, right? So I'm like, I'm always like kind of speculating. With E, I can put some numbers there, but then I don't have very good measurements, so it's also a bit speculative in this sense. Yeah.
All right. Any final
No, I
questions?
just had maybe more follow-up comment on this, but thank you for your very nice talk.
Thank you.
That probably one criterion to select the next target could also be the constraint on the distance of this source, because of course the luminosity scales as the square of the distance, and I know that for most of these systems usually the standard assumption is 10 kiloparsec, just because it's easy then to describe the luminosity. But probably besides checking, of course, the position of the luminosity in this diagram, maybe also helpful to check also those sources for which the distance is very well constrained, and then also the scattering in the luminosity
Right.
would be
smaller. Good point. Thank you. So basically, it was a comment about also checking the distance to get as a criterion to choose criterion to choose the next source. Yes, thank you.
Okay, then if you're very quick.
No, it's not a very big question, so maybe I can.
Yes.
We can talk later. Okay.
Great.
Repeat my,
We're going to be here until tomorrow, so if you have any questions, I guess you will be in my office then, so just come and see her and ask her some more questions. For the people online, if you're not here tomorrow, you can just email her and ask some more questions.
There's a
It was just a thank you comment.
all right, thank you.
Okay, then I would just suggest we thank Melissa again for her talk.
Yeah, so as Vanessa said, I'll be here until Friday, and this is my email if you ever want to send me any comments. For people online as well, if you don't have the chance to see in person, send me an email if you want to talk. Tomorrow morning I'm not here, but today and tomorrow afternoon.